Lab 5, Faraday's Law. The main purpose was to observe and record data of a falling magnet through a conductive tube, which we used an aluminum foil, and then we modeled the interaction with the use of a computational model and compared the computational model with experimental data. So the main physical principles involved are Faraday's Law, which is a time-changing magnetic field B, our source of electric fields E with a curly structure given by the equation describing the magnitude of the EMF. And then we have the magnetic fields of a dipole, which is just the equation of the magnetic field on axis, and then magnetic force, which is the last equation here. So for the first part, we found the north end of the magnet, and as the magnet falls down, we notice how it's attracted to the aluminum wrapped around the tube. So this causes the magnet to fall at a slower rate. And if the magnet falls in free space, it would fall much faster than inside the aluminum tube. So we have time in free space is less than or equal to the time to fall inside the aluminum tube. As well, we can't use a ferrous tube such as iron, cobalt, nickel, or steel because these metals are strongly attracted to the magnet, which means that the magnet would not fall down the tube, but rather it would stick to the tube walls. Then I recorded the time it took the magnet to fall down, and we have 5 different trials: the time it went into the tube and out, and then the time it took to fall. And then we could just calculate the average based on all these values. So as the magnet falls down, it looks like it glides down the tube. It has no contact with the tube walls. However, it's smoothly going down, and it falls at a slower rate than it would do in free space without the tube. And this is a result of the magnetic force having a positive upwards component. So we decrease the magnitude of the force of gravity, where we have force net equals the force of the electric field minus the force of gravity. Then we move on to the computational model, where we have the bar magnet modeled as a point charge, and then the conductive tube model as non-interacting rings. The tube has a length of 32.3 centimeters, a radius of 1.4 centimeters, and a thickness of 15 centimeters. And the magnetic moment, the one we computed in lab 3, was 1.575. However, it was expected to be somewhere around -2. So I went ahead and used my own mu computed in lab 3, but this might be one of the sources of differences between other experiments. After running the simulation, we get the images on the right. The first one is as the magnet enters and then when it leaves, and then we have the velocity versus time graph given to the left. So interpreting the simulation, we know that the magnet orientation is it's falling north face down as the image here on the right, and we know the north we have the magnetic field in the negative y direction, and it's increasing with time. So we know that the derivative is going to point also in the negative y direction, and then the negative of that derivative is going to point upwards. So we know that the I north flows counterclockwise, which means that the red part is counterclockwise, and then the south is just going to be the opposite of the north. So this means the blue is going to represent the clockwise current. And this is because just the derivative is going to point in the upwards because it's decreasing over time, and then the negative derivative is going to point downwards, and this gives us this clockwise current. When we flick the magnet around, we invert the direction of the induced currents as the magnet falls down. So we get the blue current below the red current. The blue is still going to be clockwise and the red is still going to be counterclockwise, but we see here in the images how in the north side down we have the blue on top, and then on the south side down we have the red on top. So the total timing tube of the real world system is greater than the computational system, and this is because the computational just doesn't account for air resistance, which is slowing down our magnet. So if we are able to include this in our simulation, then it would be more accurate. And as well, the shape of the velocity versus time plot tells us, first of all, the magnet starts at rest, so B initial is 0, and then the velocity increases with time because the final velocity is not 0. Then we know that the velocity versus time plot has a constant slope in the middle, which means that the acceleration is constant, so the forces acting on the magnet are also constant. However, we do see some variability at the two ends, which means that the magnet enters and experiences electric force, so it's going to decrease the velocity, and then it leaves and it doesn't see any electric force, so it becomes more steep, which means the velocity just is going to increase. So if the resistivity is close to zero, it means that the tube becomes a better conductor. And this means that more EMF is going to be generated as the current through the tube increases, causing the magnet to fall at a slower rate. And if holes or slots were cut into the tube, the model wouldn't be as accurate because it would cut the rings into different shapes. Breaking up the rings would cause less induced current to run through the tube, so less current means that the magnet would fall at a faster rate.